Oh. Yeah.
Okay. I'm ready.
Okay, so everybody, welcome to the nuclear seminar this week. So we have Evgenii Ievlev from UMN. He's going to talk about some exciting stuff about some first principle calculation in supersymmetric twisting. Everybody knows it's hard, so let's see why he can make it. Yeah.
In QCD, it's hard.
Okay. Yeah.
This is not QCD. Thank you. Okay, so this is work that I have been doing since before my PhD and still doing to this day as a part of my research, and I thought it would be appropriate for a nuclear physics seminar because it's about hadron masses. So, of course, in QCD, dealing with confinement and computing hadron masses is, well, it might be very hard or impossible. It's just, there are like some approaches like kind of Lagrangian, but they are not first principle. So you cannot just like write down for like QCD Lagrangian, start from there, no approximations, and get finite mass, proper mass. So what the rough idea that people understand, well, at least that people more or less agree on, is that like there is like some kind of flux tube. For example, if you take a pi, like the meson, there is some kind of flux tube between like some kind of confined objects like constituent quarks or whatever it is. So, and we're gonna start, that's gonna be a starting point. So of course we cannot do it in QCD, so we will make some simpler model which is in some sense solvable, where we can do this computation. And I should make a disclaimer right now, so that it's not, well, it's going to be a very distant relative of QCD. So to be honest, I have little to no idea how this approach could be like used in QCD or like what it teaches us in terms of real world QCD, but I have what I have. So, and that's what I'm going to talk to you about today. Okay, so at any point, please interrupt me, ask any questions. So a lot of technical details will be swept under the rug, but if you don't believe me on anything, please ask me questions. Okay, so that's like roughly speaking our plan. So first I'm gonna remind you about basic construction of flux tubes, monopoles and quarks. And out of these objects, we're gonna cook up hadrons and compute their masses. And the framework that I'm gonna use is a supersymmetric QCD with the n equals 2 supersymmetry. So n equals 2 means we're gonna work with extended supersymmetry. So we're gonna add. So if you consider like, say, some 4-dimensional QCD, you can like supersymmetrize it in a minimal way. We're gonna add twice as much supersymmetry to get even more nice mathematical structures.
Is that going to be the key to the predictability?
Yeah. N equals 2, and moreover, it's going to be super conformal. So, yeah. So again, yeah, it's not QCD, admittedly, but I'll tell you about what I have. And based on this plan, like you might think that we're gonna do something like that. And yeah, throughout this talk, and on the front end, you will not see that much of SUSY in this talk, but at the back end, SUSY will be the cornerstone of everything that is behind this, because of many things that I'm going to talk about today. I'm going to talk about some bosonic sector on the classical level, but then like SUSY kicks in at the quantum level, because of SUSY, you have some cancellations between fermions and bosons, and certain quantities computed at weak coupling stay exact and can be like dragged into strong coupling and as well. At the very end, if we have time, I have like, I think 3 slides to give you a rough idea why that happens in SUSY, but like in the main body of the talk, I was not planning to talk about that very much. And if you think that there is a typo in this word, There's no type because we're doing hadrons. Sorry about that.
That's what I thought.
I think it's the last
As
joke
usual.
on this talk. So now we're gonna get serious. Okay. Okay, so I'm sure you're all familiar with stuff like quad flux tubes and monopoles, but to be complete, I will remind you anyway. So the basic idea comes from superconductors. So, you know, in superconductor, we have a condensation of electric charges, and that makes the gauge field massive. There are two types of superconductors, type 1 and type 2. So roughly speaking, when you apply magnetic field, so if you apply strong enough magnetic field, it can penetrate the superconductor, but because it's massive in the bulk, it cannot just spread. It gets compressed into a thin tube. And type 1 and type 2 differ in this respect, that in type 1 superconductors, these flux tubes attract each other. And so as soon as you start forming them, they all like coalesce and form one large flux tube, and superconductivity is destroyed in the bulk of this material. Whereas in type 2 superconductor, these flux tubes repel each other, and you have a chance to observe them. And indeed, these have been observed, at least in thin films. And there is a borderline scenario, which is actually realized in supersymmetry, where these flux tubes just don't interact at all. Okay, so in the bulk of the superconductor, this flux, so again, like magnetic field gets compressed. Energy of this object is proportional to its length. And that's, roughly speaking, a starting point about thinking how to implement rigid trajectories in some setup. So you have an object whose energy is proportional to its length, and you have like linear potential. And if you see it in the bulk, it looks like you have a monopole and anti-monopole, and electric field between them gets compressed. Of course, there are no monopoles here. Magnetic lines like truly never end. They like go outside of the superconductor, but that's the starting point. And indeed, like in the 1970s, an idea was put forth, but that maybe, just maybe, something like that actually does happen in QCD. But instead, in QCD, there is like a dual picture. So you have, so if you have electric charges, condensation of electric charges, then magnetic charges get quantized, and other electric charges would just be screened. So in QCD, maybe just you have a condensation of magnetic charges, and then electric charges, which quarks, get confined. Of course, this is like electric, not in the sense of U1, but in the sense of non-abelian gauge series. But yeah, it's a rough idea. So of course, that's a very nice idea, but you cannot really check it in QCD. At least humanity have not been able to so far. This, however, this has been explicitly checked in the framework of n=2 supersymmetric QCD, which are famous works of Zabik and Witten from 1990s. So indeed, they have been able to prove that even if you start with pure supernuclear theory with no quarks, you still have monopoles there, and they condense. You get confinement of quarks. Okay, so like moving on from superconductors to field theory, you can construct this kind of flux tubes. Of course, in field theory, they're well known as Rykosov Nielsen-Olsen strings. So Rykosov is the guy who figured them out in superconductors, and Nielsen-Olsen extended this to field theory. For example, consider four-dimensional electrodynamics with some complex scalar which develops vacuum expectation value. But this is all classical level, and here you normally would see lambda, but I already tuned it to some special value. It's going to be there automatically in supersymmetric setting. Okay, so gauge symmetry is broken, so photon is massive. But if you put the theory in some boundary condition which forced some flux of magnetic field, then this flux gets compressed, and you can actually construct a sort of like solitonic object, which should be this string. So we can, in simplest setup, you can consider string which is stationary, stretched along the z direction, and you can write down equations for the string. You can solve these equations, and if the potential coupling is tuned to the special value, you can actually write down the string tension, at least exactly on the classical level. So this at this coupling, you can do something which is called Bogomolny completion. So you can write down this action. You can write down the energy function of this action as a sum of square plus boundary term, and this boundary term just gives you the tension. Of course, on quantum level, if you study only bosonic theory on quantum level, this formula is going to be modified. But in supersymmetry, it's actually, if you have enough supersymmetry, it's protected, and it stays like that, even at the quantum level. Okay, so this is a basic string construction. So string has a center moduli, which means that, so if in the orthogonal plane x and y, I can put the string in shifted parallel to itself, and energy will not change. So in the sense, a string breaks two translational symmetries. And as you know, if you break continuous symmetries, if some particular solution breaks continuous symmetries, it will give you massless degrees of freedom living on the string. So in other words, you can write down a solution for the string positioned at some point x0 and y0. So this is a real solution if these are some constant parameters. But then if you assume that these parameters can vary very slowly with z and with time, and if you plug in back this solution into the four-dimensional action, integrate over the transversal plane, you'll get what is called effective action on the worldsheet. Okay, so so this is a rough idea, reminder of a construction of just solitonic strings. Okay, but so far the strings can energy of the strings is proportional to their length, but they have nothing to confine. They cannot end anywhere, really.
Question.
Yes.
What would be different in the tension formula if you didn't tune the band like the constant?
Oh yeah, I would not be able to write down this nice analytic formula. I would be able only to compute it numerically. Okay, so these strings had nowhere to end, so they have nothing really to confine except themselves. So let's introduce monopoles. So these strings on the previous slide carry magnetic flux. So then if I assume that they can end some object, then this object should be a source of magnetic flux, and that's a monopole. So how do you construct a monopole? So most familiar setup is the 't Hooft-Polякov monopole. So you consider now non-abelian, or in simplest case, SU2 gauge theory, and you consider a scalar field in adjoint representation of the gauge group. And again, you trigger condensation of this adjoint scalar. So if I consider SU2 theory, then this adjoint index A runs 1 to 3. So you want to find the vacuum, you want to minimize the potential. So the potential minimizes when all phi squared equals to psi. And that's so if you think of this phi as three-dimensional field space, then this is equation for a sphere, right? So phi develops some vacuum expectation value, but it can be any point on this sphere of radius of square root of psi. So and then that allows you to consider objects with interesting topology, because boring topology would be that phi is just the same value everywhere in space. It's not that interesting. Interesting would be if phi takes different values at different points at special infinity, right? So we live in three-dimensional space. So roughly speaking, infinitely far away, you like see like S2 sphere. And if direction in the field space of this phi is actually like proportional to direction in the real space, and like wave of phi changes in respect to the direction in the field space. That actually, so object with this topology actually turns out to be a magnetic monopole. So yeah, so you know that like in usual electrodynamics, magnetic Gauss law, divergence of P equals 0 just forbids existence of electric charges, and you bypass the Gauss law here with a clever trick. Roughly speaking, if phi develops some expectation value, then gauge group SU2 is broken down to U1, but which U1 is it? For example, if a third component of phi is non-zero, then the unbroken photon is actually the third component of this F tensor. Right? If first component of phi has non-zero expectation value and other twice zero, then this unbroken U1 is the first component of F. So the meaning of electrodynamics actually depends on the direction in space. That's how you bypass the Gauss law. You don't just write electrodynamics. The meaning of what is your low energy electrodynamics actually depends on direction in space. Yeah. And there's some math that you can do, and that actually gives you a magnetic monopole. Yeah, so that's roughly speaking what I just said. Okay, and again, if you tune lambda to a very special value, which is 0, so roughly speaking, you consider a limit lambda goes to the 0, which you should think of as no potential, but you still enforce this boundary condition. And in this limit, you can again rewrite the energy functional as a sum of squares plus some boundary term, and that boundary term actually gives you the monopole mass. And you can write down this nice analytic formula again for non-zero lambda. Can only compute it numerically. Here I can write down analytic formula. It's of course classical formula. If you stick to this bosonic theory on quantum level, this formula will be modified, and I don't know how. But if you add enough supersymmetry, it still stays exact. Well, not in this form. Sorry, not in this form, but you can compute actually the exact quantum value of this monopole mass.
So why did you cheat?
Oh, sorry about that. There should be a G in here. Okay, so these are basic ingredients. And before I move on to N equals 2 physics QCD, are there any questions at this point?
Sorry, just to confirm, so you said you send lambda to be 0 in the, and you're just discussing like a CPM -1 model, and you do.
Oh, it's not CPN -1 model. That's a CO2 gauge theory.
Constraint.
Huh?
So if you send lambda to be 0, you just choose a value to have a constraint, the length and the constraint, and the boundary condition.
So if I send lambda to be 0, I should think of it as no potential term, but I still enforce this boundary condition.
Yeah, that's what I mean.
Right.
So are you just fixing the length then?
Length of phi?
Yeah.
Yeah, so in vacuum, phi, yeah, constrained to be psi. Yeah, so you can think of it as like two-dimensional sphere or CP1 manifold as you want. Yeah, but that's just a boundary condition at infinity. So in principle, phi does not have to stick to psi, and inside the monopole it indeed vanishes, for example, right? But I for this boundary condition at special infinity. Okay. So now let's discuss how these objects fit into the framework of N equals 2 supersymmetric QCD, and what is N equals 2 supersymmetric QCD. Okay, so as you probably heard, when you introduce supersymmetry, you need to add superpartners to your normal particles. So for example, in normal QCD, I would just have a gauge boson and matter represented by fundamental fermions. And here psi and psi tilde are two wild fermions, and a couple of wild fermions can comprise a direct fermion, right? So in normal QCD, you would just, from gauge sector, you would just have this gluon field, and from the field, from the matter sector, you would just have like a couple of psi and psi tilde. But here, adding minimal supersymmetry would require you to add to every boson you need to add fermion. The fermion you add the boson, right? So n=1 supersymmetry would require you to for each gluon you add a gluina, which is a wide fermion again, and for each fermionic quark you add a scalar partner, which is a complex scalar quark, right? Okay, so and because each flavor of quarks actually is described by two wild fermions, you add a quark for each one. Okay, then if you add twice as much supersymmetry, you need to put twice as more constraints. And in the matter sector, you can go by just like requiring another supersymmetry conformation between the fields that you already have. But in the gauge sector, you actually need to add twice more fields. So you add a second gluina. And for gluina that you already had, you need to add another scalar, so a complex scalar field. So all these fields form what is called vector multiplets. So these are like your gauge sector, and all these form what is called hypermultiplets. So this is your one flavor of quarks. Okay, so again, you have in the gauge sector, you have a gluina, two wild fermions, and a complex scalar. Of course, everybody is in the adjoint representation of gauge group. They, besides supersymmetry, these fields should transform in the same representations, gauge symmetries, or some other, well, not all, but most other global symmetries that you can have, may have in your theory. Right, and we want to consider theory which would like at least distantly resemble QCD. So we put quarks in fundamental representation of the gauge group. So these complex scalars, quarks, are also in the fundamental representation of the gauge group. And you can immediately see that the field content of the theory already is very suitable for constructing the object that I was introducing earlier. Because here on one hand, you have fundamental scalars, or scalars in fundamental representation. So if they develop vacuum exploitation value, potentially you can have strings. Yeah, moreover, my gauge group will be actually U1 crosses UN. So this U1 sector already promises you some kind of strings. We will see in the next slide what kind of strings these actually are in a bit more detail. On the other hand, in the gauge sector, you have this adjoint scalar. And as we saw in the previous slide, the construction of polytop monopoles, if you have an adjoint scalar which also develops vacuum exploitation value, you can have monopoles. So in this theory, potentially we can have both and strings and monopoles. And what we're gonna do is we're gonna build a picture where these monopoles are confined by these strings. So admittedly, in my today's talk, it's not going to be an electric confinement of quarks. It's going to be a magnetic and dual picture. It's going to be confinement of monopoles by magnetic strings. Electric strings are harder, and it's still like more work needs to be done. It's some work in progress. But yeah, there is some progress, but I'm not going to talk about today about that because it's still very raw. Okay, so anyway, let me move on to this side of the slide. So, okay, so this n=2 QCD Lagrangian is horrible. It took me 3 slides to write it down. If you want, I can show it to you. But if you don't ask me, I was planning not to show it to you and just ask you to believe me that okay, potential terms in there are such that we can, in particular, trigger. Oh yeah, and I forgot. Yeah, I will consider all quarks of the same mass m, which is again quite far from real world QCD, but that's the limit that I'm gonna take. And moreover, soon I will send that mass m to 0 and work with that. But for now, it's just m.
And can I ask a naive question?
Yes.
Why is the gauge group U1 times SU1?
Right. So
Is it Nether's famous?
yeah.
I mean, I'm worried about the U1, obviously.
Yeah. So that one piece will help us to construct strings. Maybe ask me again the next slide.
Okay.
Okay. So, right. So potential is such that this quarks develops scalar quarks, both of them, right? Develop vacuum expectation value roughly of this size. So what is here? So here, every row, every column of this matrix represents one flavor of quarks. So one flavor of quarks is fundamental with respect to gauge group SUN, so we have n components, right? And each, this is the second flavor, third flavor, and so on. And for now, just for a second, I will consider a case where I have 10 number of colors and flavors. So I can write down this scalar quarks as a square matrix, and by a matrix, and one particular vacuum like I'm allowed to consider in this theory, it's this just diagonal expectation values. The psi is some parameter that in your theory that just gives you these waves, and so that completely fixes the gauge group. So roughly speaking, this is mass of your gauge bosons, and the gauge bosons are actually gauge bosons and like Higgs bosons, and like they combine in the same multiplet. So that's actually a mass scale of Higgs as well. Roughly speaking, that's mass scale in the bulk. We have at least at weak coupling. So for now, everything is going to be at weak coupling, but we're going to go to strong coupling soon enough. Okay, so again, like this vacuum expectation value completely breaks the gauge group. It, of course, completely breaks the flavor symmetry that we had. We consider quarks of equal masses. We had UN flavor symmetry, but that's broken. Instead, the diagonal subgroup is not broken. So you can think of it like as a color matrices act by multiplication from the left, and flavor matrices act by multiplication from the right. But if you multiply this matrix by some u and get some u inverse on the other side, it will not change. The diagonal subgroup survives, and it's what's called color flavor locking.
So this is just the global symmetry of the
Yeah.
device.
Yes.
As you know.
Yeah. So, and there are actually some papers which conjecture that a similar thing is actually realized in neutron stars. We have two flavors of quarks.
But sorry, I mean, this is the vector symmetry, not the. What happens to chiral symmetry here? Is there a chiral symmetry?
Well, there is arch symmetry, of course.
Well, very naively, if I have enough flavors of massless quarks, I have an SU and F left and an SU and F right. My impression is that what you're describing is that SU and F vector, that is left plus right or something, is broken, but SU and F vector combined with color is preserved. But what I'm asking is, what about just SU and F left? This is naive. Maybe this question is too naive. Or, I mean, similarly, is there a dynamical scale in this theory? Is it a CFT? Like, what do I need to know to understand what's going on?
Okay, so there is in this case there is a dynamical scale lambda.
Okay.
As in QCD. It's not a CFT.
Okay.
As to your
Is there chiral symmetry breaking? Is there a chiral symmetry at all? I know there's all sorts of weird
There is only, okay, so there is, so, yeah, I think non-abelian, so Lagrangian is such that non-abelian piece of chiral symmetry is like broken explicitly.
I see.
You have
There's
U1
no abelian chiral symmetry.
Yeah. So you have U1 piece of chiral symmetry.
There's a U1R symmetry. So
Yeah.
chiral.
That's anomalous.
It's anomalous.
Yes.
So there's a discrete anomaly-free chiral symmetry? Like, what's the statement about the symmetries?
Yeah, that's
Do I need to know it for the rest of the talk? I'm not trying to derail you. I'm just
no.
Yeah.
It's good. I forgot. I think. Okay, yes, I think there is a discrete version of chiral symmetry, but certainly in some vacuum, at least.
Is there a moduli space of vacuum as well?
Yes.
Okay.
But I think it's in this one is going to be isolated point, and it might be just so discrete chiral symmetry, I think, acts trivially in this one. There are certainly strongly coupled vacua, monopole and diene vacua. Chiral symmetry sort of acts by permitting those.
Okay.
But that's a quark
I
vacuum.
think we should talk a bit more because I suspect there's an anomaly that should obstruct that possibility.
Yeah.
But
So
that probably goes way beyond what you want to talk about.
So yeah, that's probably will not be important today unless I miss something.
Okay.
So yeah, but we
So
should.
this breaking happens above the confinement scale. It was the
So for
confines.
if it is, yeah, so that's what I'm gonna assume at first, that it's weakly coupled. It's above the confinement scale, but then I'm gonna send psi to something like, well, not zero, but I'm gonna go to strong coupling.
I'm sorry, I
Yes.
have one more question. So like this is one thing that you could do, but it sounds like nothing is really forcing you to turn on this particular exam, other than the desire for recoupling and to preserve symmetry as much as possible. But you also have the adjoint scalar.
Yes.
You could have used that guy. You could have gone on the moduli space of that guy and Higgs down to U1 to the -1.
Yeah.
So there's some reason you didn't do this?
Yes.
There is.
I mean, there are, indeed, as you said, many possibilities here. So basically speaking, or roughly speaking, this is a quark vacuum, which means that all quarks develop vacuum expectation values and monopoles don't. There are vacua where you can, if you trigger not a condensation of some quarks, but not all, automatically that will, you run into strong coupling on quantum level, that will actually trigger condensation of certain monopoles.
Yes.
And you can do that. So we're exploring all possibilities. Today, I'm gonna tell you about one possibility.
Okay, that's fine.
Sorry, actually, so are you along the mesonic branch or baryonic branch here, right? Because this is not gauge invariant, right? So you should be writing gauge invariant operator here so you can specify which branch you're on.
Right. So
So where are you?
good. So that's roughly well. It's an N=1 terminology,
Yeah,
but
I'm
I think
I'm
I'm.
because that's what I know. But
I think
I'm not so familiar with this,
yeah.
but it seems that
So-
there's got to be a gauge invariant here. There's got to be mesons and baryons, right?
Yeah. So that's
So to get fit.
mesonic branch. That's not baryonic branch, I think.
No, but there's got to be a gauge invariant that gets a vacuum expectation value, right?
Yeah. I mean,
So is it
you
a
can
meson?
write a bilinear of this Q.
So it's bilinear, so it's more like a meson then.
Yeah. So that's like a yeah.
Sounds like
So
a
you
meson.
can you can do that. I didn't write it down because I didn't want to overcomplicate things. But maybe on the contrary, I should have written it down. But you can write like some bilinears of Q, which would be gauge invariant and parameterize your expectation value. But
So that breaks left, right, play the symmetry to this diagonal.
I think that's broken already at the Lagrangian level. Left, right. I mean, like to left, right to the vector.
Because of the mass, is that what you're saying? Huh?
because
I'm
of
sorry,
some
no,
Yukawas.
I'm sorry, that makes my question about chiral symmetry very stupid. I'm so sorry.
It's I
I
think
forgot you had a mass.
it's because of Yukawas. It has like a lot
Oh,
of
you have
Yukawas.
other Yukawas.
It's like yeah, it's
Right,
yeah,
so you don't get non-abelian chiral symmetry even when m is 0.
Yes.
That's the-
yes.
I'm sorry, very naive question. I
Mm.
think I lost that. The bottom line, so why do I have U engaged symmetry multiplied on the left
So
to the Q as you said?
you're asking about this formula.
I know, I'm just asking. So in the bottom line, you said, okay, I have a UN gauge transformation acting on the left of the Q,
Yeah.
and SUN acting on the right.
Yeah.
So my naive question is, why do we have SUN gauge on the left? Well, how should I understand?
Yeah, yeah. So again, so here like I schematically write down all the quarks flavors in the following way. So the first row is the first flavor.
Okay.
This is the second flavor.
Uh,
Right. So what does gauge symmetry does? So each flavor has n color components. It transforms as a fundamental. And when you have a fundamental representation matter, it acts like as if you have a gauge matrix and you have a row. If you should want your flavor, just multiply. So that's what, like roughly speaking, fundamental representation. And in this, yeah. Okay, so I think I made too many slides.
Sorry.
No, it's okay. The questions are great. Questions are great. Good. Okay. Right. So, okay. So, as I was advertising, since we have matter in fundamental representation, and we trigger its Lakem expectation value, we can have strings. This is an example, not on, but like an example of an ansatz that you can think of it as being a string. So when you have a maybe I forgot to mention that, well, at least in a certain gauge, when you have the Abrikosov-Nielsen string, the complex scalar field that you had there, the Wein's infinity, picks up phase. You go full circle, and here, again, it's a gauge-dependent statement, but in some gauge, you can say it like that. Gauge-independent statement would be, okay, I have magnetic flux. So, and here I choose one of the quarks, scalar quarks, to wind at infinity, while all the other will be not winding at infinity. And that's a most elementary example of a string they can have. I could have also considered a normal Abrikosov-Nielsen string that would be having all of these quarks wind with the same phase around infinity. But that turns out to be not the most elementary thing, string that we can have. It has n units of magnetic flux, and to have a string with minimal possible magnetic flux, and we use that. Okay, and I forgot what your question was on the previous slide, which
I don't know. So
Yeah.
Why there is a UMN page?
Huh? Yeah, you one piece. Yeah. So if you didn't have that U1 factor, you couldn't just say that again, my last flavors, just my last flavor wines. Because roughly speaking, that winding is a combination of overall U1 winding and some Cartan combination that cancels winding in all the other flavors. So, and that will actually ensure stability of the string at the end. Well,
if you didn't have a gated one, you could still do this, but this would correspond to something like a global string.
yeah. So
You don't want that. You want it to be local.
I want locals because the global string has discussed previously. They have IR divergences, which I don't
That's fine.
want.
That's fine. You want it to
deal
be a
with.
local string. That's fine.
Okay. So, and remember on the previous slide, we had this nice global SUN symmetry, but that particular string solution breaks it down to SUN -1, which still can act on this piece, and U1, which can act on this piece. So again, you had some continuous global symmetry before you consider any strings, but as soon as you introduce a string, it actually breaks it down to some subgroup. The quotient is actually it gives you what is called the modular space. So what does that mean? So again, remember that for usual abrikosov-Nielsen string, I could like shift it in the like orthogonal xy plane, right? And that would not change the energy, right? And that gave me two moduli corresponding to the center of the string, right? So in this xy plane, I could put a string at some like other place with the coordinates x0, y0. And this x0, y0 are just like parameters of my solution. And energy just does not depend on these solutions. These are called module. Okay, so it turns out, so roughly speaking here, I could have I could ascribe some winding to this flavor instead of the last flavor and some other flavor, or do some more interesting combinations. So roughly speaking, I could act with this SUN symmetry on this solution and get some other solution with exactly the same energy. So that gives me actually some parameters. And that one formula tells me that these parameters actually live on certain manifold. So I'm going to explain a bit more what that manifold is on the next slide. So that's an elementary example of a string. And again, string tension on the classical level is just like 2 pi xi or something. And the quick coupling, I can just write it down the formula. And then it actually stays exact when I go to strong coupling quantum. Okay, so let's talk a bit more about modular space and effective theory on the string. So what I want to do, I want to consider worksheet of the string, worksheet theory of the string. So that means that so if you have like a guitar string or something, if it's stationary, right? But if you push it, if you deposit some energy, it like gives you sound, right? So there are like waves propagating along the string. And the like spectrum of these waves and how they interact is the effective theory on the worksheet of the strings. Worksheet means that I have the theory of this on the string is two-dimensional, so it depends like these modes like depend on time and but also on the coordinate along the string, which for example is. And I want to construct this theory. So what are the ingredients? Again, of course, like you have two translational modes, which are like modes like which correspond to the string bending, right? So it is just this trivial piece, and that's not particularly interesting, but will be important later. But then I also have this interesting internal moduli which do not correspond to real space. They correspond to some degrees of freedom which lives on the string and takes values in this manifold. So roughly speaking, so here I like depict it with some arrows, and these arrows can slowly vary along the string. So these are this moduli, and geometrically, what is this modular space? So you consider complex n-dimensional space, and well, roughly speaking, you do the following. So the space, you can think of it as having, as a sphere. First of all, it's like a sphere in n-dimensional complex space. So here I have like some a number of these complex fields n with index L, which runs from 1 to n, and I have some constraints. So sum of squares of these fields should be a constant, and I gauge weight overall phase. So initially I had 2n real degrees of freedom, minus 1 constraint, minus 1 overall phase. So that's going to be 2 times n minus 1 real degrees of freedom living on the string. And you probably know that if you have some field theory where fields cannot take just arbitrary values, where fields live on some manifold, this is called the sigma model. So the effective theory on the string is going to be actually CPN, sigma model. So, and that's like sort of like symmetry argument how to arrive at this formula. So you can do this more or less rigorously. Actually, in the framing of the theory, you can just like write down at weak coupling, you can write down a solitonic string solution. You can then parameterize it by your moduli. Then you assume that this moduli weakly depend on time in Z, plug it back into the 4-dimensional Lagrangian, integrate over transversal plane, expand in derivatives. And on the 2-derivative level, you will arrive at this formula and you can derive quite rigorously. But here I just give you like a symmetry argument, but roughly speaking like that. Yeah. And here, the formula that I wrote here. So what ingredients come here? So as a sigma model, you can write the Lagrangian in a nonlinear way, then with some quartic terms in N. Here also, like linearize it, I introduce some auxiliary gauge field. It doesn't have a kinetic term, so if you integrate it out, you will get back to the nonlinear formulation. But and this sigma is another complex scalar, which is there. I think of it like as some scalar to introduce masses, and it is it doesn't come from any symmetry argument that I can think of, but it comes there because of supersymmetry. Okay, and then there are like some high derivative terms, and then there are also some fermion terms which I didn't write down because it's a supersymmetric theory. But
Is sigma parameter or field?
the sigma is a field. I mean, it's an auxiliary field, doesn't have a kinetic term.
Okay, what about ML? The parameter?
Yeah, this is a quark masses. Yeah, I should have erased in Excel because I took them all equal, but this is just like comes from 4-dimensional quark masses. Okay, so then, as I said, because we had an adjoint scalar right here, can also hope to find monopoles, and indeed there are monopoles in this theory. Oh, I forgot to mention, yeah, well, a few more things. Okay, in this theory, so this moduli on the classical level, this is some like continuous symmetry, so you can expect to have some massless degrees of freedom, like degrees of freedom corresponding to the translational symmetry, these waves propagating. But actually, when you go ahead and quantize it on the quantum level, there's some dynamical scale generated, which is because of supersymmetry, it actually turns out to be equal to 4-dimensional lambda scale. Yeah, so these fields become actually massless, and the back end, what happens? You have some chiral anomaly, continuous chiral anomaly, which continuous chiral symmetry, which is actually anomalous and broken down to some Zn symmetry. And I stress that that's a supersymmetric CPA sigma model. So in non-supersymmetric CPA model, different story. Here you have then exactly degenerate ground states on the worldsheet. So and then you can have kinks interpolating between these ground states. It is a very discrete number of them. So how do you interpret this in terms of 4-dimensional theory? So each vacuum on the worldsheet is actually corresponds to a certain type of string in the bulk. Turns out that on the quantum level, you do not have like some continuous continuous possibilities for strings in the bulk. There are like n kinds of these strings. That's it. And the kinks on the worldsheet respond to different types of the strings coming together to form some kind of junction. And there is like some particle that lives on the junction. And what that particle is, it actually is a monopole. Remember that these strings carry magnetic fluxes. So the junction, the theme the object that these strings attached to must be a source of magnetic field. And that's like a rough depiction. There are like SUN magnetic fields, UMN magnetic fields, and monopole changes. Yeah. It's forced. Okay, so in the bulk I have 8 supercharges. So on the in the voltshed is going to be 4 supercharges. So 2,2. Yes.
It's not enhanced in the infrared.
Mm.
No?
In this case, no, it's large enough. Yeah. Okay, so and I didn't tell you much about that, but actually there is like another parameter in the box. I mean, like if you can consider quarks of not equal masses, but like wildly different masses, then there would be like no this clever symmetry, but still you can do a similar construction. And if you start with quark masses which are widely different, actually bulk is weakly coupled, and you can just construct Hoof-Polyakov monopoles. But when you send these quark masses to be the same, this sort of magnetic fields become more and more compressed into thin tube, and monopole becomes more and more quantum, and eventually it forms like objects living on the string. And the hadrons of this theory are actually these kinds of objects. These are so this is like a meson, this is like a baryon, these are like necklaces of these monopoles. Okay, so that is all well and good, and supersymmetry helps us as far as to write down a tension of this like infinitely long string, and the supersymmetry can tell us what the masses of these monopoles are, even in the highly quantum regime. But unfortunately, it cannot help us to compute masses of this object, because infinitely long string is a protected object, what's it called, the BPS state. Like monopole on this like infinite string is also a BPS state, but when you start bending these strings really hard, things go bad. So this object, like mass of this object, is not protected by supersymmetry anymore. Of course, it's this object is going to be a part of like some supersymmetric multiplet, but it's going to be what's called a long multiplet. Its mass is unfortunately not calculable. Strong coupling, and moreover, this 3-red dot that I wrote here. Remember that I said we do a derivative expansion. This is just a 2-derivative level. Of course, that's a good approximation when your string is approximately straight, but bends only slightly. When you start bending a string like that, you can imagine that higher derivative corrections kick in, and it's hard to deal with this theory.
First, why do you call this hadrons?
Yeah, so well, these are compact objects formed by confining some kinds of other things, and
It's the wrong confinement now. Confinement, it's magnetic confinement, it's like a superconductor.
yeah, that's why technical term for this is instead of confinement mechanism. Yeah, so but it's similar.
Is it? I mean, so sorry, I'm not just being nasty. I mean, for example, in a baryon, for various reasons, we expect to be bound by a baryon vertex kind of string, like a Y-shaped thing, not or its generalization to higher n. So actually, while that's the generic expectation from long string effective field theory and so on, seeing some confirmation of this, some test of it explicitly from Susie would be great. I have no idea how to explicitly explore this in QCD. But here it's somehow very different because we're not dealing with actual baryons. Don't get me wrong, this is interesting. It's interesting.
Yeah.
It's just it's akin to working in the Higgs regime of QCD, that is to say in the color flavor locked phase, which you alluded to earlier. But
Right. So as to Y-shaped
Yeah.
string in the baryon, well, I think like a picture with one string in meson is already speculative enough.
Yeah.
Picture with Y-shaped string in baryon is might be
Fair enough.
well, I'm only saying that picture is like probably as good as yours.
I'm sure it's the correct answer in this case. I'm just saying that in QCD, I think there are reasonable arguments for why it should be more like the.
I
It
mean,
should be a baryon vertex.
this is a okay. This is a valid comment,
Yeah,
but
it's not what you did. I understand. You did.
it's not QCD, unfortunately.
Yeah.
So okay, I have okay. So let me continue. Maybe I'll run a bit, maybe 10 minutes past the deadline. So what happens if you add flavors? If you add more flavors. So now consider the number of flavors is more than number of colors. So remember they were equal previously. So what happened? Well, actually it turns out that okay, your gauge group is still completely fixed. But not all the quarks actually become massive. So despite the fact that you had this mass parameter for quarks in the Lagrangian, there are like a bunch of other fields that enter Lagrangian as well, and some of them develop vacuum expectation values which can shift that mass, and some number of flavors actually become massless. So you have massless fields in the bulk. What that means for a string? So string, you still have a string. So gauge group is still completely fixed. So if you enforce having some magnetic flux, it's still compressed into a tube. It cannot just spread out. But because you have massless fields in the bulk, the fall off of the profiles of the string is now not exponential, it's power law. So, and you can imagine that as soon as you have some power law fall off, what for example like scalar profiles, you must have some scale parameter for that power law. That parameter is actually turns out to be another modulus that lives on the string. And again, so this you can derive this result, but it's long. So I ask you to believe me that what happens is that instead of that constraint that we had in our CP1 sigma model, you add a few more moduli rho, and that constraint is modified in the following way. So the target space becomes non-compact. So in particular, you still have NC number of this moduli n, where NC is the number of colors. But then if your number of flavors exceed the number of colors, you'll start adding this other moduli, which are also complex fields. So now you have some number of these fields, some number of these fields, one constraint, and you still gauge away the overall phase. And then, well, let's consider a particular example. The number of colors of 2 is 2 and number of flavors is 4. What happens then? Then how many degrees of freedom do I have? So this is like internal module in the string, not related to real space. So you have, when NC is 2, you have 2 complex scalars n, so which is 4 real degrees of freedom. So NF is 4, and F minus NC is 2. So you have 2 these scalars. So again, 4 real degrees of freedom, minus 1 constraint, minus overall phase, minus 2, you have 6 internal degrees of freedom. 6 plus 4 is 10. If you're familiar with string theory, you know that's a magic 4. And the rest of my talk was going to be about that. So are there any questions at this point? Let me quickly flash through the rest. Yeah, at least let me give you a flavor. Okay. So let's look more closely at this example with 2 colors and 4 flavors, and with this formula 4 plus 6 is 10. I'll explain it. So first of all, Well, you probably have seen this formula for the beta function of monobillion gauge series. And if you plug in all the supermultiplet content that I have shown you before, carefully compute it, you'll find out that when the number of flavors is twice the number of colors, beta function is just 0 on one loop level. And wonderful NSVZ formula tells us that beta function is one loop exact in this area. So if it's 0 at one loop level, it is just 0. So gauge coupling does not run. And you have potential for superconformal symmetry.
Oh, I'm sorry.
Yes.
Is it flavor equals to 2 or color equals to 2?
So color equals to 2, and flavor is twice number of colors is 4.
Oh, that's a multiplier.
Yeah.
I thought it's a comp.
So in the bulk, you still we still keep this parameter xi, which is dimensional parameter, which is the scale of scalar quark waves. So you don't have conformal symmetry because you have a dimensional parameter in the bulk, but you will have superconformal symmetry on the volume. Xi does not penetrate the volume. Only quark masses penetrate the volume, but you set them to 0. You do not have dimensional parameters from the volume at all. Okay. Okay, good. So now remember string tension is xi and the bulk mass scale is g times square root of xi. Xi is the scalar waves. So, well, at least naively, you can say that, okay, if I go to strong couplings and g to infinity, maybe bulk just decouples, but tension still is constant. And the size of the string is well, at least like some size of the string core, at least is controlled by these bulk masses. So you can conjecture that, okay, a strong coupling, I might go into a situation where my string becomes very thin. And well, again, that's a naive statement. So like in strong coupling, this formula is modified. But it has been conjectured that this is true, that the string actually becomes thin at certain point in strong coupling. And there have been a few checks and checks out. So what that means for effective theorem, the whole shit that all these like high derivative corrections just get suppressed, and all you end up is a two derivative theory on the whole shit, and that's kind of exact. Okay, so why do you need thin string? So that's the potential to consider it as a fundamental string in string theory. Okay, then as you remember, I told you that if you have infinitely long string stretched along the z direction, it has two translational degrees of freedom corresponding to shifting the string left and right. But if you consider closed string, which is more compact, it has like 4 translational degrees of freedom because each piece of the string can move in space. So total number of degrees of freedom that lives on the string worksheet is 4 from the real space and 6 from the internal degrees of freedom. That adds up to 10. And 10 is a magic number because superstring is self-consistent in precisely 10 dimensions. And by 10 dimensions, I just mean that how many sort of like fields live on the worksheet. They don't have all to be real space dimensions. So but they can be. So what people normally do in string theory, you start with 10-dimensional string, which really does live in 10 dimensions and 10 real space dimensions. 6 of them you just compactify on a Calabi-Yau. What happens here instead is just interpretation is different. 4 of your dimensions are real space, but 6 are actually some internal degrees of freedom that happen to live on the worksheet. Okay. Moreover, if you again write down a constraint from that sigma model, so you see again, like you have it's 6-dimensional manifold, it's a Calabi-Yau. So surprisingly, well, turns out it's a Calabi-Yau. It's non-compact Calabi-Yau. It's called the conifold. Yeah, maybe I'm going to tell more about that, but okay. It's non-compact, but it is a Calabi-Yau. which is very nice. So, and our theory to start, it was parity preserving. And judging from that, it has been conjectured that it actually is a type 2A superstring on a certain Calabi-Yau. Yeah, and in principle, as soon as we figured that out, closed string spectrum should give us hadron masses. So if you remember hadronic initially, how did string theory emerge? It emerged as a like attempt to describe even it was even before QCD, I think. It emerged as the attempt to describe mesons as like sort of like stringy objects. Well, people more or less quickly realized that okay, in 4 dimensions you cannot do it, and it sort of diverged from this like head-on description of hadrons. But now it's like in a sense like resurrected in this sense, but in supersymmetric setting. Okay, maybe a couple of more.
Sorry, but this closed string in 4D, it can't have any gravity in it, right?
That was the next.
Very good question. Yes. So of course, since we started with super young Mills, we did not have any gravity. It would be very stupid if we got gravity. Very fortunately, you do not. So okay, I will. Can I like 2 more minutes? 5 more minutes.
So I don't know. I mean, I think
Okay.
it would be good at some point soon to wrap up, just because we've already exceeded the normal boundary condition.
Good. Yes.
I know we have lots of questions, but
We have 5 more minutes.
at most.
At most, yeah. Okay,
I
couple.
mean, ideally, we have time for questions before.
Okay,
Okay.
2 more minutes.
Okay, I don't know. We have lots of questions. 2 more minutes is.
2 more minutes.
Sorry, I just
Okay,
don't.
I'll just
Okay, if anybody feels like they want to leave, please don't be shy.
Yeah.
Like if you gotta go, you gotta go.
2 more minutes. Okay, so I'll just tell you about massless. Yeah, so how is this different from normal string theory? So in normal string theory, you do what? You compactify on some compact Calabi-Yau. So moduli of this Calabi-Yau give you massless fields in low energy, which can like pick up masses or some other stuff. But all the massive states are just KK modes, which are like completely decoupled because the Calabi-Yau is very small. So what happens here is, yeah, and every modulus of Calabi-Yau gives you a massless field. What happens here is not the same because of non-compact nature of this Calabi-Yau. So first of all, not every modulus gives you a field, because to have a field in 4D, you need to, like, roughly speaking, integrate over this like 6-dimensional Calabi-Yau. Because of its non-compact, not every wave function normalizable. And what happens here is that there are like 2 possible. So, like this, we did not invent this manifold. This manifold has been known like for a very long time. String theorists love it because it's a toy model for Calabi-Yau singularities. But anyway, there are like 2 possible moduli on this manifold. One of them turns out to lead to non-normalizable wave functions on the Calabi-Yau, and that's actually this coupling constant of the sigma module. And the other one gives you massless fields. And you can check that spin 2 fields necessarily has a mass. If you try to construct massless spin 2 fields, it just does not exist because it's not normalizable. No graviton. Okay, then okay, good. So you can like figure out massless states, and this has been, at least this massless existence of this massless state has been checked by us also. Field theory considerations. But then if you want to construct massive states, okay, so string theory is very good, but still hard. So, and supergravity approximation actually doesn't work because our Calabi-Yau like becomes singular at the strong coupling point. So, but the theory of single Calabi-Yau fortunately is also very known. And anyway, this turns out to be L flush through this, equivalent to certain Liouville CFT, for which the spectrum of all the primary operators is known exactly. That turns out to be, very fortunately for us, exactly solvable model. So we know the spectra and how it's related to 4D masses, and so you get masses of 4D hadrons this way. Okay. So yeah, you can like try to generalize and introduce quark masses. So that's roughly speaking work in progress. And again, like to reiterate, so this is not QCD admittedly, but like you know this joke about man who lost his keys in the dark, but he's searching under a light pole because it's light here. That's the only place that he can look for keys, despite the fact that they're not there. So that's what we are doing, but yeah, we do what we can. Thank you for your attention. Okay.
An infinite number of questions, but I can't resist just one more. This all seems to work for 2 colors and 4 flavors, but if I change number of colors, number of flavors, it then.
Right. So
Okay.
it's actually on our recent paper. So first of all, you actually can generalize 4 colors, 8 flavors in an interesting way. So you just keep half of your quarks massless and the other half just prescribe them some very large mass M, and the theory actually splits into 2 sectors. Each of them separately is describable by this like superstring. But then if you then send this mass difference to 0 to really recover this theory, again, like surprisingly, it turns out to be a dual to 2-dimensional black hole in which this parameter plays the role of a black hole mass. And again, it's an exactly solvable model, so you can get the hadron mass. Turns out hadron masses will not depend on the, well, at least to some approximation, hadron masses will not depend on the quark mass splitting, but hadron multiplicities will, at least to some approximation, which we are still figuring out what that approximation actually is. You can use another work in progress, but there is like one paper that's already out on that. So beyond that, yeah, we have some thoughts about how to move beyond that. That's even more raw for now.
Can you go back, because you flashed that real quick, your main result. It was the mass.
That one.
Yeah, this was the main result, right? This is that's the masses in your, that's the hadron mass.
Yeah. So that's a scalar sector.
Yeah.
Formula for like higher spins would be like different. I think it's also okay. So despite the fact that it's exactly solvable model, it means that you in principle can write it down all the masses, but it's also not an easy task to do, but it's doable. So I think for now we have only scalar and spin 2 states masses, but we don't have higher spins.
But this is just using conformal invariant, so, right?
Yeah, there is like also some, well, not CFTs are exactly solvable. There is some underlying, it's called Katz-Moody algebra that allows you to actually get the spectrum of primary operators, right? Because like for some random CFT, you're not guaranteed, even because of, even if you have conformal invariance, if your CFT is complex enough, it's not guaranteed that you know all the spectrum, all the operators. But here you actually can write it down. Of course, supersymmetry is like essential, and superconformal analysis is essential for this. Yeah, but we need actually a bit more symmetry on top of that. And fortunately, we turns out to have that a bit more in this instance. Okay, so yeah, so maybe it has been long enough. Sorry about that. Yeah. Yeah, I should have made even less slides. Okay, thank you for your attention.
What is the string complex? Which is the gauge 3 parameters?
One second.
In your simplest example with 2 colors and 4 flavors.